Welcome to lecture 18 of Power System Protection course. So in the last lecture, that is lecture 17, we covered many aspects of distance relay, because we discussed regions for inaccuracy of distance relay reach. There are many regions we discussed, like how the transmission line parameters affects, how the error in the CT and PT measurement that affects the underreach and overreach problem. So there are many aspects we discussed, and then we talked about the requirement of the three-step distance protection scheme. So why it is essentially required in order to avoid the overreach, particularly of the distance relay when it is set at 100%. So because the overreach is the probability of overreach is very high, therefore we need to set it at 80 to 90% of the total line length, so that it will operate accurately. Therefore the three-step distance protection scheme came into picture. And then we discussed how to implement this three-step distance protection scheme, and already we saw for single-ended line, single-fed transmission line, and the lines fed from both the side. We talked about that, and then we discussed the trip contact configuration for the three-step distance protection scheme. So different the trip contacts, how it will be arranged, those things we have discussed. Then finally we discussed the drawbacks of the three-step protection in the double end fed lines. So what are the drawbacks? Because only 60% of the line is in fact protected instantaneously. So when the fault occurs within that 60% of the line, like we can see here in this picture, right, three-step protection scheme, we can see here that this is a double end fed lines. Both the side we have sources, and this line, our main objective here is to protect this line AB. So therefore both the side we have relay, distance relays. And now if we'll see, and these protection schemes are three-step protection scheme. So when we'll see that this 60% of this line is instantaneous, it is in fact instantaneous, it is giving the instantaneous protection, right? And other 40% it is not, because for 20% towards the line end A, it is instantaneous, because relay A will detect the fault within this, but it is from the end B, it is not instantaneous, there is some delay. And similarly 20% towards end B, the relay B will in fact operate instantaneously, but the remote relay A, which is remotely placed from the fault location, that will in fact operate in delayed manner, right? So that is how we can see the three-step schemes. This is for relay A, this is for relay B, right? Okay, so Z1, Z2, Z3, how it is set. Already we discussed all these aspects very in detail, elaborately last class. And so in this there are these are the drawbacks. From remote side it is difficult to operate instantaneously, therefore there is a mismatch of operation that is not synchronizingly, it is both the relays are operating. So that will cause in fact problem. So therefore let us see how to avoid this kind of problem. Okay, further, so already we discussed this. If the fault is at end A and within 20% of the line, then RA will respond instantaneously, whereas RB will respond to this fault with a time delay of T1. And similarly if the fault is at end B and within 20% of the line, then RB will respond instantaneously, whereas RA will respond this fault with a time delay T1. So that means your isolation of this line when the fault is happening within the 20% of the both the end, the isolation is not happening instantaneously. It takes some time, because first the relay operates at one part and the remote relay operates with a time delay. So that in fact causes problem. So therefore we need the carrier aided protection, as I told in the last class. Through the carrier aided protection, both the relay operation can be synchronized just by transmitting the information from one end, from the local end where the fault is happening, to the remote end relay, right? Okay, it is always possible. So let us see types of the faults generally happens in the system, in the transmission system. In the electrical system, generally there are three types of fault happens. One is your transient, semi-permanent and permanent. And if we will see the statistics of occurrence of these faults, then the transient fault happens most of the time. So what is transient fault? It is around 80%, the probability says 80%. So what is transient fault? In fact, transient fault is not permanent in nature. It happens for temporarily for few milliseconds sometime, right? And it is because of the ionization of air outside the insulator. It is not the insulation breakdown, in fact it happens because of the air breakdown, because of the ionization effect of the air. It happens after breakdown. The fault happens temporarily when there is a certain overvoltage, and when the overvoltage is removed, then it is stopped. So therefore, how to tackle this? In fact, this is tackled using the reclosure scheme in the protection methods. So there is reclosure approaches. So when as soon as the fault happens, the circuit breaker opens and recloses again just after few milliseconds, right? So then as it recloses, if the fault has been removed and the air across the insulator deionized, then what happens? It remains in the closed position. The circuit breaker remains in closed position. If it is semi-permanent, then also the circuit breaker recloses for few times. Then if it happens that it is not working, then if it is transformed to the permanent fault, then your circuit breaker keeps remain open, right? So this is how the operation happens. So therefore, the scheme is, in practice, the scheme is first, as soon as the fault happens, because most of the faults are transient in nature, so the reclosure scheme is implemented. So as soon as the fault happens, the circuit breaker is allowed to again reclose. So it may be auto reclosure using the scheme of auto reclosure, or manually it is reclosed, right? So then if the reclosing is not sustaining, again it is opening because of the existence of the fault, then it actually goes to the permanent fault. Then it is considered a permanent fault and the circuit breaker remains open, right? So therefore, typical deionization time we give for the auto reclosure or reclosure of the circuit breaker for different types of the different levels of the voltages. For 66 kV, generally the typical deionization time is 0.1 second. So after 0.1 second, in fact, the reclosing phenomena was allowed. And in 132 kV system, the typical deionization time is 0.17 second. So that means after 0.17 second, the reclosure is allowed, auto reclosure or reclosure. So for 220 kV system, the deionization time is 0.28 second. Similarly, as the voltage level will go on increasing, your deionization time will also go on increasing, right. Similarly, for 400 kV system, the deionization time increasing to 0.5 second, right. So that means when it happens, your fault happens, that means at the both the end the circuit breaker should trip very instantaneously. Even if we will see the 220 kV line, it should be, your circuit breaker should trip within 0.28 second and again it should reclose, right. So therefore the both the end circuit breaker should instantaneously operate, instantaneously become open and again reclose. But if your 3-step scheme is used and we are using the local measurements for both the end, then it is difficult really to isolate the line instantaneously, right, within 0.28 second, very difficult, unless we go for the carrier aided protection, right. So therefore here the necessity of carrier aided protection is very essential, right. So therefore we go for carrier aided protection, right. So it is very essential. So what is this carrier aided protection? We will see then, okay. So now already we talked about this little bit, we can see here, right. So already we saw this line is a doubly fed line and your 60% of the line is protected instantaneously. That means any fault happens within this 60% range of the line, so your line will be immediately instantaneously isolated and then the reclosure phenomena takes place. But when the fault is here somewhere or here somewhere, right, so then what happens, then obviously at the local end of both the side, then one breaker will trip instantaneously but other breaker will have delayed operation. So that means your line is not going to be tripped instantaneously, which is the requirement for auto reclosure or for reclosure scheme, right, because most of the faults in practice are transient, around 80% of the faults. So therefore it is very essential that this, whether the fault is towards the end or towards the middle, it does not matter, but the line should be tripped immediately, instantaneously, and both the circuit breaker at both end should trip instantaneously, right. So that is the requirement. So then how to make this possible? If we can send the information measured at suppose the fault happens at this point at the local end towards A, then if we can transmit the signal, that is voltage and current seen by the relay VR, let us say VR and IR both, if we can transmit very quickly to relay B, right, and relay B can process these informations, then instantaneously relay B also will operate very instantaneously, very close to the relay A operation, right, very it is effective if your transmission of the signal is very quick, and it is possible only through some carrier, right, carrier signal. Through the carrier signal we can transmit the signal VR and IR, though these informations are very small amount, small volume, we do not require very high bandwidth to transmit, but the transmission should be faster, right, that is the essential requirement. So now you can see right here you can see that as the arrow indicates, if we can transmit the signal very quickly to relay B from local end of relay A to the remote relay, right, similarly from relay B to the remote relay A, then it is possible to synchronize the operation of both the relays and both the relay can operate instantaneously, right. So this can happen. So this in fact through some carrier channel. So generally in the transmission system we use the PLCC link, right, okay. So now let us see what are the carrier schemes we can use, right. So there are various options for a carrier. So let us see what are the options and what are the requirements in fact. So the protective relays process information contained in the voltage and current at the local end, right. So always the relays process these informations at local end. The nearest end has the clear cut information where the fault is happening. The nearest end of the fault has the clear cut information which is so difficult to extract using the power frequency, current and voltage at the remote end. So therefore remote end it is very difficult to get that information very quickly using the power frequency, difficult, right. So if we could somehow pass on this small amount of information from one end to the other, it would enhance the quality of decision making at both the ends. Somehow if we can transmit or pass this information to the other end, right. So we therefore need some carrier to carry this information. Therefore it is essential to have some carrier signal to carry this information. So what are the various attributes of an ideal carrier channel? Let us see, it is listed as follows. We can see here that the delay involved in the communication should be small, right, compared to the time period of the system frequency. If your system frequency at 50 hertz, then the delay should be much more less than the 20 millisecond. That means your communication delay should be very much less than 20 millisecond. That type of communication scheme we should choose. Since only a small amount of information is to be passed, the carrier channel need not have very high bandwidth. So we don't require very high bandwidth, but we need a faster channel which can transmit the information very fast, right. Faults on the power system should not adversely affect the functioning of the carrier channel. This is one of the requirement, or you can say in fact attributes of the carrier channel, right. The power system should not adversely affect, whatever fault happens, it should not affect the functioning of the carrier channel. So the carrier channel should be under full control of the utility company, right. This is one of the requirement. The carrier equipment such as carrier transmitter and receiver should be protected from the high potential of the EHB line. So that means sometime we have also studied in our UG level that there are electromagnetic interference of the EHB line and the telecommunication line. Therefore the carrier channel should not be interfered or should not be affected by the high potential of the EHB line, right. The carrier channel should be economical as well. This is very important. So being engineers, it should be the main criteria. It should be economical. It should not be very costlier. So let us see various possible carriers of information for relaying purpose. What are the possible carriers? Let us see. So first option is your leased telephone line. Leased telephone line from the telephone service provider. If we will take this, what are the benefits? Running cost is very high, maintenance is a problem, right. Okay. Running cost is generally very high for telephone line, and the maintenance cost is also a problem. Maintenance is a problem, and guarantee of quality of service may be difficult to obtain, right. And second option we have is terrestrial microwave communication channel. Either it is owned by the utility or leased. Okay. So for that, frequency range is between 3 to 30 gigahertz, very high frequency. The range of communication is line of sight, right. A large number of antenna towers are required for this. Therefore initial investment and maintenance cost are both very high. This is from cost point of view, it is very difficult to consider this terrestrial microwave communication channel like mobile towers, right. Okay. Though it provides very large bandwidth which may be shared with other data communication services. It has advantages, it has large bandwidth, right. Then your third one is your satellite communication using VSAT terminals using geostationary satellite at 36,000 km. So, the frequency range is between 3 to 30 gigahertz. Propagation delays involved are of the order of 2 into 36,000 km by 3 into 10 to the power 5 km per second. So, that is the propagation delay is around, this is your length and this is your speed, right. So, then it will become 240 millisecond, that means 12 cycles. So, this is therefore not permissible because the time of propagation is very large, it is around 240 millisecond. We need a channel carrier channel which can in fact transmit the signal within very less than 20 millisecond, right. So, then last option is your power line carrier communication, right. So, power line carrier communication, it is the most economical since power line conductors used for this purpose and it doubles the physical medium for carrying the carrier signal, right. The physical medium is very large and the carrier signal is a signal of much higher frequency compared to the power frequency which is coupled to the ESP lines. So, in this scheme the carrier signal is coupled with the ESP line itself and like I have shown you in the classes of when I was discussing the potential transformer CVTs. In the CVTs I have shown the trap wave carrier, right, carrier wave traps. It is being used like the tuning of capacitances and inductances, right, which is also used in the potential transformer and simultaneously it is used to trap the carrier wave, right. Okay. So, that in fact contains the information. So, that is the power line, we call it power line carrier communication. So, frequency band allocated to this service is 50 to 200 kilohertz. Thus, the carrier signal frequency is just above the audible frequency range and just below the medium wave radio broadcast band. Due to moderately low frequency of the carrier, a small bandwidth is available. So, because the carrier frequency, the frequency of the carrier signal is very less, not very less, it is moderate. So, the bandwidth available is less as compared to bandwidth available in case of terrestrial microwave communication channel. However, protective relaying does not need a large bandwidth, we do not need large bandwidth. So, what is important is the delay involved which is very small in case of power line carrier. For example, a 1000 kilometer line will cause a delay of 0.33 millisecond which is very less as compared to the 20 millisecond which is the time period of the power frequency signal, right. Okay. So, therefore, this is the most suitable channel through which the information can be transmitted, because we do not need a very high bandwidth to transmit the signal, because we have very less volume of information to be transmitted and the delay is very less as compared to the terrestrial microwave and satellite communication, leased line, telephone lines. So, therefore, power line carrier communication is the best suitable channel through which we can transmit the information of voltage and current to the remote end relay, right. Okay. So, therefore, no need to go for, because it has other advantages that the carrier signal can be embedded in the transmission line itself, right. Okay. So, therefore, we should go for the power line carrier communication. Okay. So, this is all about your distance protection schemes. and now we will see the differential protection schemes. What is differential protection scheme, where it should be used, and also how it operates, what are the major drawbacks, we all will discuss in these classes by talking about the differential protection schemes. Let us start today differential protection scheme, then in the next class onwards we will elaborate more and more. Okay. So, this is the basic block diagram of a differential protection scheme. If we will see that any equipment, suppose we want to protect the equipment, so this is here and we want to protect this equipment. Now, how we will protect? Just by putting two CTs across the equipment, both end of the equipment, and putting an overcurrent relay here. The connection scheme we can see here, and suppose in case here is the load, here is the source, and here some equipment we want to protect like transformer, bus bar, right. So, in order to protect, this is the basic scheme, and let us consider two ideal CTs, right, with the ratio, CT ratio is n is to 1 and same CT ratio, and under normal load condition, if we will see normal load condition, what happens? So, we have two circuit breakers across the equipment, suppose it is a transformer, right. Now, your CT will bear a current of IL by N. What will be the direction? So, direction will be based on the dot convention, right. So, let us put the dot mark, and at both the end, when the current, the dot rule says that, already you know this in your machines class, right. When the current enters the dot at the primary side, okay, and that means the current should go out at the dotted end in the secondary side. This is the rule. When it is entering at the primary side at the dotted end, it should go out at the dotted end of the secondary side. Okay. So, therefore, if we will mark the dotted end like this, okay, then two dotted ends. So, primary of the CT is your line, right, transmission line. So, this dot is here and the other dot at the secondary side is here. Now, when the current is entering at the primary side at the dotted end, so the current will go out at the dotted end, right. Similarly, as the current is going out here at the dotted end in the primary side, right, your current will enter here at the dotted end in the secondary side of the CT. Now, I can see that if the current flowing here is the load current IL in the primary side, this is your IL, okay. Now, at the secondary side the current will be IL by N, because the CT ratio is N. So, IL by N will flow in this direction and it will go through and it will again enter here at the dotted end of the CT, and that is same current IL by N. Therefore, the current flowing through this relay, we call this current as spill current, okay. Current flowing through this relay, this overcurrent relay will be 0 under normal load condition, right. So, therefore, this is an instantaneous overcurrent relay and the clock setting is IPS. So, the spill current will become 0 here in this case, right. So, therefore, the relay will not operate, and that is why the under normal load condition it will not operate. It is supposed not to operate. So, when it will operate? When there is a fault inside the equipment, or we call it internal fault, right. Even to the external fault also, suppose the fault happens here, what will happen? The current remains same at the in the both CT secondaries. So, therefore, the spill current again here will be 0. So, therefore, again the relay will not trip and the circuit breaker will also not operate. Okay. So, now suppose we will consider a fault, external fault, as I told. External fault happened here outside the CT, two CTs, And similarly, if we will find the current in the cities, here the city current will be If external by N, and here the city current will be If external by N, and both the current will be flowing in the same direction. Therefore, the spill current will become 0 here, and therefore, your equipment is safe and it will not trip. And if your fault is outside, then the relay somewhere here it will operate, and the fault will be isolated, the faulty part of the system will be isolated, right. Okay, so this is how to the external fault the differential protection also does not respond. And if the fault is internal, so what happens? Let us consider an internal fault with a current of If internal. Then if your current is, the load current is I2, then what happens? Your current in the left hand side of the equipment, that is I1, will be equal to load current I2 plus If internal, because the fault current is If internal. So therefore, the current flowing through this city secondary will be I1 by N, and that is nothing but equal to I2 plus If internal by N. And in the right hand side of the equipment, if you will see, the current flowing here is I2, right. So because of that, the current entering into the city secondary is I2 by N, right. Okay. So therefore, your spill current will be this current, this I1 minus I2, right. Sorry, I1 by N minus I2 by N, right. So that is nothing but If internal by N. So if this If internal by N is greater than this clock setting of the relay, overcurrent relay, then obviously this relay will trip. This relay will give the trip signal to the circuit breakers, both the circuit breakers, and hence your equipment will be isolated. Okay. So this is how it operates. It responds to the internal fault when the internal fault happens, not to the external fault and the load current, right. Okay. Let us see the zone of protection of the differential relay. So in this we can determine how much the zone is contained within which, when the fault happens, the differential relay will operate, right. So here we can see that the zone is between from one city to the other city, right, where the cities are connected, right. So therefore, the zone is defined from one city to other city, and any equipment for protection under this zone is put inside and connected through this transmission line, that will be protected by this differential protection, right. For external fault, both the side external faults, this relay will not operate, as we discussed all these things. Whenever there is an internal fault inside anywhere inside these two cities, right. So then that is called the zone of differential protection, right. So this zone of differential protection is defined like this. Okay. Then the relay will operate when the fault is inside the zone of the differential protection. Let us see the actual behavior of a simple differential scheme. Whether it is whatever we have seen till now, it is the ideal behavior of the cities, ideal behavior of the differential protection. But let us see the actual behavior, whether it in fact acts like that, because we know that the cities never operate under ideal condition with ideal ratio, right. So even if we put the same city ratios, both side n is to 1, but still it will not operate, because both the city will have some phase error and the ratio error, right. So because of that phase error and ratio error, we will have the difference of the secondary current. So IS1 will be never equal to IS. So that let me write in a different manner. So it will be never equal to IS, which is equal to your IP by N, right. Okay. And here also IS2 will be never equal to Is, that is equal to Ip by n, right. So why it doesn't happen? Because of the ratio error and the phase error, right. So therefore if we will consider n as the nominal CT ratio, n1 and n2 the actual CT ratios, these are the actual CT ratios, because considering the phase and the ratio error, then what happens, right. So already we have talked about, already we discussed in your lectures related to CT, we have discussed with this this equivalent circuit. Let us talk about it again. So this equivalent circuit is, we can see here, this equivalent circuit is having JD, RS and XLS, that is RS and XLS are the secondary side resistance and the leakage reactances, and JD is your magnetizing impedance, and already we talked about why the primary side resistance and reactances are neglected, right. So now if we will plot the phasor diagram considering VV as the reference, then if we will plot IB will make an angle with VV lagging angle, right. So then I can plot IBRS and JIB XLS, and this will give me ES, right. So what is ES? ES is here. This is your ES, right, already it is shown. So this is your ES. So now your magnetizing current, let us say the magnetizing current is I, and which is lagging to ES. So because this is this is inductive in nature, so therefore it approximately it will lag by 90 degree, and by summing of I and IB, by making the summation of I and IB both, we will find IS. IS is here, that is the secondary current, right. Okay, this is IS, that is the actual IS that needs to be flow, right, in the circuit. But instead of IS we get this current IB, right. So therefore whatever angle difference will be there between IB and IS, so this IS is your ideal secondary current, right, ideal secondary current, and this is your actual secondary current, right. So therefore the whatever the phase difference will be between IB and IS, that we call phase angle error, and the ratio error will be identified by from the magnitude of IS and IB, right. Okay. So that already we talked about in your previous classes. So your IS is in fact IP by N, and your IB is not equal to IP by N. IB is different, right. Okay. So IB in fact is IS minus IE. So now if we will just plot what will be the current in spill current here, right. So that is nothing but IS1 minus IS2, right. Okay. So IS1 is IP by N1 theta 1, and IS2 is IP by N2 theta 2. So what is this theta 2 and theta 1 exactly? We will see in the phasor diagram by using phasor diagram, and N1 N2 is exact actual CT ratios, N is your nominal CT ratio, right. Let us see how we can. So your IS is in fact it is equal to IP by N. So N is your nominal CT ratio, right. And now if we will plot IS1, so IS1 is IP by N1, the magnitude of IS1 is IP by N1, but the angle it is making with IS is theta 1, which is shown here, right. And similarly if we will plot IS2, IS2 is here IP by N2, the magnitude, and it is making an angle of theta with IS, making an angle of theta 2 with IS. So that is the phase angle error of CT2, and this is the phase angle error of CT1, right. So this is how these are represented. Okay. Now if we will find the spill current is not exactly the difference of the magnitude of the IS1 and IS2, it is in fact the phasor difference between IS1 and IS2, right. So this will give me the spill current, right. Okay, IS1 minus IS2. It is not the magnitude difference of the currents, secondary currents, but phasor difference of the secondary currents. Okay. So let us stop here for this class, and we will continue in the next class the through fault stability and stability ratio, because it will take more time to discuss, and we will talk in the next class in your lecture number 19. We will talk about this through fault. What is through fault stability and stability ratio? Through fault already we know, the external fault is known as the through fault, right. And what is in fact through fault stability and stability ratio, we will see in the next class. So thank you very much for your kind attention.